What if I told you that time doesn't tick the same for everyone? Imagine two identical clocks, one on a spaceship zooming through space at 90% the speed of light, and the other resting on Earth. The clock on the spaceship runs slower compared to the one on Earth. This isn't some sci fi fantasy, it's a reality rooted in Einstein's theory of time dilation. According to his special relativity, the laws of physics remain constant for all observers, and the speed of light is the same, no matter how fast you're moving. Now, let's break this down. Picture a moving train. Two observers, one on the train and one on the platform, see light differently. For the observer on the train, light travels at a constant speed, while for the one on the platform, it appears to take longer. This discrepancy leads us to the concept of time dilation, where time slows down for fast moving objects as perceived by a stationary observer. So, if our spaceship travels close to the speed of light, the astronauts on board experience time much slower than those of us on Earth. Now, let's dive into the famous twin paradox. Imagine twin A stays on Earth while twin B embarks on a journey to a distant star at near light speed. When twin B returns, they find they are younger than twin A. How can this be? Both twins see the other's clock running slow. The key lies in the fact that twin B changes frames of reference during the journey, accelerating and decelerating, while twin A remains in an inertial frame. This asymmetry resolves the paradox, showing that time dilation isn't symmetrical. But what about real-life evidence? Consider the muon decay experiment. Muons created in the upper atmosphere should decay before reaching Earth. But due to their high speeds, they survive longer than expected because time slows for them. Then there's the Hafele-Keating experiment in 1971, where atomic clocks flown around the world lost nanoseconds compared to those on the ground. Even GPS satellites must account for both special and general relativity to provide accurate positioning. Now, let's ponder the implications of time travel. Technically, traveling to the future is possible. If you journey at relativistic speeds and return, you'll find yourself younger than those who stayed behind. This opens up fascinating possibilities for deep space missions. Time isn't absolute. It bends and stretches based on your motion. Einstein revealed that time travel to the future isn't just a theoretical concept. It's a phenomenon we observe in our universe. So, the next time you glance at your watch, remember, it may not be ticking the same for everyone. Switching gears, let's explore quantum entanglement. Imagine two particles separated by billions of kilometers, yet they act as if they're connected. This phenomenon, which Einstein famously dubbed spooky action at a distance, challenges our understanding of reality. In the quantum realm, particles exist in a superposition, a state of probabilities until measured. When two particles interact in a specific way, they become entangled. Measure one and the other instantly adjusts, regardless of the distance between them. Einstein believed this was impossible, arguing that particles should only be influenced by their immediate surroundings. This led to the EPR paradox in 1935, where Einstein, Podolsky, and Rosen challenged the randomness of quantum mechanics. They proposed that either information travels faster than light, or particles somehow knew their outcomes. Enter John Bell in 1964, who proposed a test to determine if quantum mechanics was correct. His theorem suggested that if entangled particles produced results that couldn't be explained by local hidden variables, then quantum mechanics was indeed valid. Decades later, Elaine Aspect's experiments confirmed Bell's predictions, showing that entanglement is real and non-local. Since then, numerous experiments have validated entanglement. In 2015, scientists closed major loopholes in these tests, proving that entanglement isn't just an artifact of flawed equipment. The 2022 Nobel Prize in Physics recognized the groundbreaking work of Aspect, Clauser, and Zeilinger, who even achieved quantum teleportation, transferring quantum states over long distances. So, what can we do with entanglement? Quantum teleportation allows us to transfer the state of a particle without moving it. Quantum key distribution creates ultra-secure encryption. If anyone tries to intercept the entangled pair, the system detects it. The future may hold unhackable communication and global quantum networks, all thanks to this spooky phenomenon. Quantum entanglement challenges our deepest understanding of reality, breaking the rules of locality and cause and effect. It opens doors to a future that's not only faster and more secure, but also stranger than we can imagine.